All right, so now we will try to specialize what we've been doing so far for the past few classes on the convergence. So we've been looking at convergence. We have set things for general f as long as they were del f del square f existed. Now let's try to focus on when f is convex or strongly convex. So for today's class, we will be interested in just the normal gradient descent, which is xt minus eta times del f. Right? That's my simple algorithm. What do I want to do is to look at convex function and try to see what convergence guarantee I can give. Okay. So to do that, first assumption we're going to make. Function f is smooth. That is del f of x minus del f of y is less than equal to times. All right. Okay. So what do we have? F is convex, beta smooth. And the problem we're trying to solve is minimize f of x. X belongs to unconstrained. Okay. My algorithm, I have frozen to gradient descent. For different algorithms, you'll get different guarantees. All right. So what do you think is going to help me? Now I have convexity, I have beta smoothness compared to the previous two classes where we did not assume anything with convexity or smoothness. So where do you think the gain is going to come from? If anyone has an idea, otherwise we'll proceed. Why do you expect things to be nicer?
Beta is not necessarily integer.
Beta is what?
Not necessarily integer.
I didn't say anything. So what's the only condition you need here? You know Lipschitz condition, right?
Uniform.
No, what is, so suppose I only ask for function f to be Lipschitz, then I would not have a gradient. I would simply say f of x minus f of y to be less than L times. So there is.
You were talking about so means you were talking about like how the
Gradient is
the
beta
gradient is changing.
Lipschitz. That's all. Okay, so the guarantee I want to prove is the following. And in particular, the interesting thing we are going to do is we're not going to select step size either by the line search or exact line search or by Armio rule. We'll try to show something even with a fixed step size, which is independent of how the function is behaving as these iterates change. So we'll keep eta to be constant. So this is called a constant step size convergence. And for that, we will show as long as f is convex and beta smooth, we'll be able to show convergence. This is not true always for an arbitrary f.
Yeah. We can it's a constant thing, and we can use this.
Of course, we will use.
Because we can divide by beta.
We're saying it's one line proof.
No, not one line proof, but something on those.
No, it's much more involved than that.
I think I am missing something. So
okay.
I just wanted to know that so it does it allows that the function will not have a point where it is not differentiable or something? Like,
If I'm saying something like this,
spike, like,
this first of all, if it exists, right? Otherwise, I can't even say this.
that is, if F dash, I'm talking about F dash.
Yes, it's smooth means what? It's Lipschitz. Think of in the gradient space.
Yes.
All I'm saying is that function is Lipschitz. Forget about this. Think of G and G of X and G of Y. In G space, it is Lipschitz. That's all it is. So whatever you get by Lipschitz is whatever you get here. Nothing more, nothing less. You never seen the smooth definition. Surprised.
Like, you're saying smooth, so I just.
This is what smoothness is. And why the word smooth? You can think about it. Why is it smooth? It's controlling something even stronger. That's precisely why it is smooth. Okay, so the result we're going to prove is the following. For some reason, Boyd doesn't care about this. So this is not in Boyd. But it should really be the first result you should prove. Let F be convex and beta smooth. Then gradient descent with constant step size. Beta equal to 1 by beta satisfies the following. F of xt minus f of x star is then equal to 2 beta minus x star over something rather strong. So what kind of convergence is this? You define ourselves some different forms of convergence. This is order 2. Why? There's no order 2, it's quadratic, right? That's what. Yeah, okay. Why is it order 2?
Because you have a constant, so it's 2 minus 1.
That's not much of a problem.
Oh, no, it's not.
What is x1?
The starting point. Anyone? We define in terms of xt minus x star, but it's not too much of a stretch. Now we're only after wrapping it with respect to f. We're asking for f of xt minus f of x star. So you could appropriately extend the definition here.
So we need to compare a t minus 1 and t.
That's all the point, right? So it's still linear. There's nothing but than linear. Okay. So prove this after proving certain properties of convex and smooth functions. So is the result clear? What are we after? And importantly, this is a constant step size. So we're not doing line search or army-ho rule, which could be costly. Here it's very easy. So as long as I know beta, so you should have asked this question. Who will give me beta? So I give you a function f and claim that it's smooth. Now how are you going to find beta? You would like to be smallest beta possible. Right? But as long as you can come up with an upper bound, things are okay. So you should always check how am I going to get this information, because I use that to run my algorithm. So whatever we do, it will suffice to get an upper bound. So even if you can come up with an upper bound, it will just reflect badly in your guarantee. But the proof will work. All right, so lemma. Not lemma 1. Wanted to put a column. Let f be a beta smooth function on Rn. No convexity here. Then for x comma y, f of x minus f of y minus gradient y transpose x minus y. What do you think this should be less than equal to? Can you guess it? Smoothness definition is clear, right? The gradients are Lipschitz. That's what's both.
F of y plus that delta f transpose y times x minus y is an approximate, like it's like a line, right? Like a secant.
Yes.
Not a secant line, it's a line segment passing through. Like,
Yes. Go on.
then
You've been doing this forever, right? Keep writing f of x in terms of f of y plus transpose x minus y plus something. What is that something? Hessian, okay. Fine. So Hessian, somehow that Hessian will relate it to the beta. That's the whole point for beta small. We'll get essentially beta by 2 x minus y. So no convexity assumed here.
Yeah, we're getting that gradient to
Here in this lemma, no convexity.
lemma in the previous one.
Why are we going back to that? This lemma stands on its own feet. Okay. All I'm using is that function is beta smooth. Okay, so how can we prove this?
f of x will be
See, all I'm given is beta smoothness. So somehow I have to convert this as some gradient of f something minus gradient of something. So can you think of that? How do you write the left-hand side as gradient of something minus gradient of something?
very roughly you have
Any idea is fine.
f of x minus f of y.
Yes.
By x minus y, but x and y belong to R. So f of x minus f of y in R it will be
It's okay.
yeah, f of x minus f of y by x minus y times x minus y. And if you take y approaching x,
Yes.
then you would get delta, like you get the gradient at x.
Mm-hmm.
And so then you would have that gradient at x minus gradient at y times x minus y.
Okay. So at least a ballpark, right? Okay. Now can you fix it?
So we can take f of y to be equal to f of x plus Taylor expansion. F of y is equal to f of x plus gradient at f of gradient at like.
But both will not cancel if you do that. If you do that, one f of x and one f of y will survive.
Yeah.
Somehow you want to write all of this in terms of what you actually started. You would like to get rid of these f of x and f of y's. So how do you, like, whatever you're saying, how do you make it precise? Another hint is, can you write the left hand side as an integral of something?
So, if the integral, the upper limit is y, x, lower limit is y. Gradient of f x tilde dt minus.
That is already in the gradient form. I don't have to worry about it. Okay, so
Equal of the gradient of f of a, and gradient f a going from y to x.
okay. There are alternate ways in which to write it. So take the integral from 0 to 1. This will help you. And write this as gradient of f y plus t x minus y, yeah. Okay, times x minus y dt. It's exactly evaluate this. There's just a trick to write this appropriately. So all of this is nothing but f of x minus f of y. And I'm going to write this as it is. This is just your LHS. Okay. Now what can I do?
You could take a the del f bounded.
Del f is bounded.
It's not a smooth. So you can take the supreme over 0 to 1 and take it out. Okay.
All of this.
Just the first year.
Okay. What will happen then?
Then it will just with the integral like supreme will arrive in some point xt in between 0 and 1. So that will be del f of xt, the integral 0 to 1 x minus y dt.
All I want is an upper bound. Don't you see an obvious thing to do before that? This is something times something. All I want is an upper bound. What is the first thing you would try? It's an inner product, right? What's an upper bound on an inner product? Yes. So that's, if you do that, what will happen? See, x minus y will essentially get as common. That's the trick. So if you use Cauchy-Schwarz, you'll get x minus y common. What will this term be? This is simply transpose y. What is the remaining term? But I can put a 0 to 1 integral to this as well, because this is not a function of t. I would just simply put a dt outside with an integral from the outside. What is the term here?
Modulus of
Mod of del f
plus 3x plus 1.
Okay. Now what? What do I know from the beta smoothness?
Okay, that is like beta less than beta, strictly less than beta mod x minus 2.
So less than equal to beta times the integral remains okay. And how do I get the half? There's a t here. How can you miss the t? It's not just simply x minus y. There's a t times x minus y. And this is equal to theta by 2. Which one? This one. Why? Beta smoothness. I didn't put strictness. If I have, that's a mistake. So just a trick, nothing else. All you have to do was to write is f of x minus f of y in appropriate form. Let's just apply beta smoothness. So this holds without using convexity of f. All right. Shall we move ahead? Okay. So if you combine and throw in the fact that f is also convex, how much can you strengthen this inequality? So for the moment, I've not assumed f to be convex. But if I give you that for free, what can you enhance this inequality to? So this inequality is, let's say, 1. For a convex function, what happens to the left-hand side? That's all I can do. Because that's always a positive quantity. So that's all we'll get if you also throw in that f is convex. So now if I evaluate, so let's say in addition, f is also convex, I get f of x minus f of y minus so what is my one-step improvement in the gradient descent? If I was at x, I go to x 1 minus beta del fx. What does the inequality tell me in terms of this is the new function evaluation compared to f of x? What am I getting from this?
You get that, let us if we substitute this
Mm-hmm.
as x and x minus, take y equal to x minus.
Okay.
Get that it's less than or equal to
Now tell me.
beta by 2 1 by beta square mod of that.
Square. Did everybody get it? Why is that true? So all we are doing is we are applying this inequality to the gradient descent update. If you don't say it, tell me you don't say it.
It's like the whole analysis. Right? Sorry.
This is some minus f of x. Is that what you're saying?
But you know, gradient.
I don't know. You just said something, I wrote it down.
Oh, no, I was saying the whole analysis.
All of this is less than equal to this.
Yeah, because it is
That's okay. What do I want? I want this. Is this true? What did you substitute y with? What was y for you?
X minus 1.
Okay. If you do this, what do you get under LHS? But that's in the wrong direction.
Okay, so if X is the other way around.
Okay, so what do you want?
X is relation to y.
X is this. X is equal to x minus this. Okay. Okay, and y is equal to x. Okay, what will you get?
X minus 1 by the gradient of x minus f of x
Yeah.
minus gradient of f of x
Yeah.
times
See, the meaningfulness of this inequality should be clear. We are after controlling how much is the improvement you're making in one step of gradient descent. Sorry? Yeah, what is that term? And that term is very important. Because
So the term that is
see, the first thing you should have checked is it better be negative. Because if I can't show it to be negative, then something is going wrong. So that was your first clue to look at the equation. It better be negative. Right hand side is not negative. So the only way to make it negative is coming from the third term, which is going to move to the right hand side.
Yeah, that is basically the gradient of F transpose X A times 1 by beta the gradient of X.
Okay.
But that will not come. Oh yeah, that will be negative.
Are you following? What is going on? Let's do it long form. This is definitely incorrect. So let's just erase all of this. Can I erase all of this? Wait. So what do you do? Okay. So what do I want? I want to write x as something and y as something. What is your option? 1 minus beta del fx and y is equal to x. So what is f of x? Is 1 by beta minus f of x minus del f transpose x. X is x minus 1 over beta del f of x minus x less than equal to beta over 2. This difference is simply 1 by beta square del f of x square. How much is this quantity? This goes away. minus and minus plus. You get a plus, so this is as it is, plus del fx by beta less than equal to 1 by 2 beta del fx. You get your minus 1 by 2 beta. See, the first thing you should click was that better be negative. So what do I get? F of x minus 1 by beta del f of x minus f of x less than equal to minus 1 by 2 beta. Minus is very important because you have to make an improvement as you progress. Okay, so let's call this equation number 2. Top name something is not clear. Pretty elementary. Most of the proofs are pretty elementary. Let's call this 3 and let's call this 2. Because now we're using convexity as well as smoothness. Lemma. If equation 2 holds, then for all x comma y belongs to Rn, f of x minus f of y is less than equal to del f x plus 2x minus y minus 1y beta. So all really we have to do is to evaluate 2 at a special point. That's it. Should I go back to 2? 2 is in this form. There is no gradient here, which is what I'm asking now. All you really have to do is to use 2 at a particular special point. That's all. Because this is true for all xy.
So in the beta school, we have that gradient of x minus gradient of x less equals to beta minus x minus y, right? So if we have the negative sign there, so like if we move, instead of there was x minus 1 whole square, right? If we move more smaller number there, then it is also the inequality will still be capped, it will be bigger.
Okay. Are you convinced?
Huh?
Are you convinced or just throwing a stone at it?
Like if we have the beta small,
Of course, equation.
then there is nothing. Like if we just leave that fact.
But look at the lemma. What does the lemma say? Lemma says equation 2 holds. I'm not really demanding beta smoothness, whatever.
We have the beta smoothness, right?
In this lemma? No.
Okay, not in this lemma.
All you're saying is equation 2 holds. Then this is also true. Why it holds? Well, there was a reason that if it was beta smooth, it held. I'm not allowing you to go back to the first assertion. In between, we proved something for ourselves. As long as that equation is true, I'm asking that this better be true. I will check what you're asking after the proof is done. That does it with the negative sign up work or goes in the wrong direction is all needed to check. But for the time being, all we have to do is to evaluate 2 at a special point. That's all we have to do. So what is that special point?
If equals to x and y equals to del x minus del y plus
Let's choose a new variable z to be equal to y minus this quantity. Okay. What do I have? Y of x minus f of y can be written as just adding and subtracting f of z from it. So f of x minus f of z plus f of z minus f of y just by adding subtracting z. Okay, what should I do with this now?
loving that.
Yeah, so what will happen to the first term? You can do it twice, right? Apply 2 on this and apply 2 on this. What will you get? The first term less than equal to some derivative times something. What is the derivative? What more? Is that all you will get?
First,
The gradient at zero.
Okay, but do I need it is a question. F is also convex.
you assume convex.
Oh. Okay, it is correct.
Oh, okay, suppose it was all we had was 2 holes. Then what?
Total modulus. You haven't finished that completing the
Sorry,
you haven't finished the line, right? Or there will be another more one more.
I want to claim this is true. Because the way Z has been defined, if I get something in X and Z, I won't get the result I want. So what is the inequality to?
F of x minus f of z minus the gradient times z times x minus z. Do less than or equal to beta by 2 x minus z.
Right. So how do I get rid of it? Is it possible to get rid of it?
You can always do like f of z minus f, like in the modulus itself, you use f of z minus f of x minus gradient of f of x and x minus z. No, and z minus z.
Z is special. Z is not arbitrary. Leave as an exercise for you guys to figure this out. Yeah. And we'll move forward. You're okay? Okay. So supposing this is true, how do I proceed further? I want to prove this. What terms are to my liking? What terms are not to my liking? Can I write this as del f of x times, I want x minus y. To do that, what do I need? I'll combine these things. Okay. What remains? Plus this part is clear. Why is this true? This becomes this.
Substitute z.
This is just substituting for z. Nothing interesting for him. Okay. I still need a minus sign here. See, the whole point is that this is something a minus, as a plus would be trivial. So what is okay and what is not okay? Yeah. So how do I take care of this?
That's also, you just replace by y minus z. Right?
Yes, exactly. There's nothing more going on. There's nothing but the same form with a minus sign and 1 by beta.
So minus 1 minus plus.
So this will be minus 1 by beta. This will be plus 1 by 2 beta. So you'll get.
Yes.
It's actually equality. Yes. By substituting. Something is not correct. Sign. So what is f of x minus f of del f of x? So look at y minus z.
Y minus z is plus 1 by beta.
Okay. So y minus. No, it should be.
Z minus y and then
No, just make sure that all the pluses and the minuses are right. So this should be a minus. And see, x minus y has already been combined. Right? So then why is it quite correct to put it there? Is this exactly correct? Let's just check one by one. This is 1 by 2 beta. This is correct. Now from here, how do I get here? If I were to take x minus y common, what do I get? Del f x minus del f y times simply z. Why is this y minus z? Right?
No. When you are adding del transpose f transpose del of f y.
Yeah.
Del of f transpose y minus of that, there will be a plus of that.
Okay, so that's correct. So this term has been added. Okay, fine. So this times minus y was absent.
Yeah, you are right.
So del f x times y is not here. So that has been subtracted. So that has been added also. Now what about this? This was always there. So this with a minus is correct. And z came with minus fx. So that's correct. So an extra addition has been made here. A by adding and subtracting.
Minus will only clear when you are doing
Yes.
minus x.
Sorry?
When you are doing f y minus x, then only the minus.
No, but you have to check what remains, right? Z remains with what sign is the question. So it should be Z minus Y. Because Z multiplies f of y with a plus sign. So that is plus, correct. And then this is the minus. So this is actually correct. So
Last one is plus also.
we'll fix that. But at least so far, this is correct.
Yes.
We'll go one by one. Okay, so now, why is that a minus is the question.
Yeah, exercise that.
Give me 1 second.
yes, so y minus z is fine. So y minus z we get minus 1 by
I made a mistake here. My mistake. of y minus f of x. So everywhere I should make sure. So now z minus y is how much? Z minus y is minus 1 by beta f of y minus f of x square. So why is this?
Is that minus will not affect anything in the last one?
Yeah, so this will be the same as, because of the square that remains the same. So now what do I get here? Now this should be fine with a minus. Yes, okay. So sorry for that trouble. Fits in.
Y minus.
This one?
Yeah.
No, this one is
Y
correct.
minus.
That's correct. It's only the final time when I put y minus z. Now what do I get? I get a minus del fx minus del fy, and that's why it works. Sorry for that. Good. Okay, so we have now number 4, 3, 4. What is our goal finally? We want to prove something with respect to, in each iteration or the kth iteration, starting from our initial choice of x1, how far we are going towards x star in k steps. That's what really we are after. In one step, we saw what was going on. Where did that go? Here. The decrease is there. Now, how can I use any of these things I've developed to, in fact, prove my result? This is what the result I want to prove. So forget about this part. Can you show it's 1 over t somehow? That would be enough. We'll do this, but at least get a sense that why it is 1 by t. What have I shown in one step compared to where I am in one step? So much in decrease is happening. This is one step, right? One step of iteration gives you so much.
So then we like take, then the second, we add all the steps to them.
Mm-hmm.
So you have, so that let's say that x is x1. And we
Yes.
So f of x2 will be x minus 1 by beta.
Correct.
Gradient f of x1.
Yes.
And so then, well, then you take x3 is equal to x.
Correct. Yeah.
So to just keep adding all of them together.
Mm-hmm. Will that be sufficient?
No.
This is true. In every step you're getting, so consecutively you can add these things up. That's what you're hinting at, I guess. Think of a recursion you can build in terms of the error. So error is compared to the optimum. What's your function value at a particular iteration? That's the error you would like to control. So what you would like to control is something like, let's call it f of x minus f of x star. Let's call it delta s. Okay, that's the error. How is this error propagating is the question. What do I know in one step what has happened? Let's call it s plus 1 minus f of xs. How much it was? Well, then equal to minus 1 by 2 beta. This much I have shown already. So what kind of recurrence relation can you write with respect to delta s?
telescopic sum?
That won't be sufficient.
Like what, like you have, I remember that in the 11 you have x1.
Yeah. Start with x1, yes.
So,
Mhm.
if you have the telescopic sum,
Yeah, but what will you get? You will end up
no,
getting.
we will take the limit of s as well as infinity.
Yeah, but all this will be addition of what? Gradients. You'll need more. And that's why you built whatever we have done so far. So first try to write down a recursion with respect to delta S. So delta S in terms of S minus 1. What is the best relationship can you write? So this is trivial. So delta S plus 1 is less than delta S minus this quantity. Does everybody see this? This should be trivial. We just subtract
Fs term.
from both sides. Is it clear or not clear?
Okay.
Now, what can you do with this? So if I want to get rid of the gradients and instead have some function of del S and the distance from the optimizer, is there a way to do that? You can use any property of F, convex, smooth, whatever you want.
So if we just look at del f s
Mhm.
square,
Yeah.
if we just do that del fx del of fx square less equals to del of fx s minus fx1
Mhm.
plus like
So using the,
triangle inequality.
are you first using the smoothness?
Yes.
Okay. What will you give you?
So basically, I wanted to use the fact that we have inequalities in terms of that
Mhm.
del fx minus del fy,
Okay.
and with respect to the x minus y, having a beta.
Okay.
Relationship.
Mm-hmm.
So to build that, and the x state is unknown for us.
Yes.
The x iteration, but we know the initial point.
Yes.
So if we just use the triangle inequality
Mhm.
in the last term, so that the del fx minus x star fx del fx minus del f1 x1 plus x fx1 del fx1.
So what will be the end result?
So the first one we can use the inequality.
Agreed. So what will be the end result after doing all this? What will you get which will prove what we want to prove? That the goal should be clear, right? What do we want to prove? That the error after t steps is going down is 1 over t. How are you going to achieve that by using that? That should be clear. You can do so many things with it, but
Yes. So
Right.
how that we will come?
from the side, what does convexity tell us? The delta S is less than equal to what? Delta S definition is f of xs minus f of x star.
Gradient term.
What? Just write that. Just by pure xs, right? By simply convexity. And what is this at most equal to? Just by the Cauchy-Schwarz. Right? Not the square. Just right? All right. So now, any idea what has happened here? So I know this is also true.
Yeah, we can put that. Like if it's less than or equal to delta S minus
Mhm.
delta S is also less than that, we can substitute
When can I do that?
when it's convex. When it is simple.
Sorry?
Yeah, because we can use that some. Yeah, so that will be. You can write it as del.
So this we have not proven yet. All we know is the gradient descent direction f of xs minus f of xs minus 1 is less than equal to 0. That's all we have guarantee with respect to gradient descent directions. We have not proven this. There are two distinct things. So suppose this is also true for the moment. So let's call this A, B, and C. What do A, B, C together give me? Is it clear what I'm asking? Okay.
Since if we have that extra xx minus e is decreasing, extra is decreasing, we can choose a key positive such that small positive such that xx minus extra is smaller than that.
Yeah.
And
but that won't help you think about it. It's not a limiting argument in any which way. What are we after? We are after proving that after time t steps, the distance has gone down by 1 by t. It's not a limiting argument of that sort.
but for the time being, we can replace the substitute b in a.
You can do whatever. I've given you A, B, C are all true. A and B we have proven. C I'm giving you for free. I'm not saying what you're saying is wrong. Will it help you proving what you want to prove is the question. So what will be the form of A you will get if you combine B and C? That's the most important thing. How can you write A when both B and C hold?
Delta s plus 1 is equals to delta a into something.
Delta S. Okay, I don't know how you touch that, but go ahead.
Basically, I am substituting delta fx by delta s by x minus norm of x s minus x transpose.
It's much easier than that, right? All you really have to touch is this part.
Yeah.
So you get to 1 by 2 beta. From here, what do you get?
Delta s square.
Delta S square divided by xs minus x star.
Now you can take a delta s.
Why do you have to go further? Just apply C. What does C say? It's decreasing. So what can I replace this with? Remember, what proof do I want to show? That compared to where I start, so I can essentially replace this with x1 minus x star, because this quantity is only smaller than that. Lots of minuses and 1 over, so always be careful about how many times it is shifting signs. Just applying B.
Delta square.
Just applying B, you get here. All right.
Okay.
And applying C, you get delta S minus 1 by 2 beta delta S square over x1 minus x star. That's a fixed quantity. I don't have to worry about how that is changing, whatever is happening. Now look at this recursion. This is a pure recursion in terms of S's, delta S plus 1 in terms of delta S minus something times delta S square. Now, what do we want to show? We want to show that this quantity is looking like 1 over T times this times beta. So, all of this will go into 1 over that and divided by S, essentially in terms of SS. Which proof do you want me to do first? This one or that one? C. Oh, let's do C. Now, why do you think this is true? But in particular, it should be non-increasing. See, this is not given by an algorithm. Always be clear. By a descent algorithm, all we are guaranteed is f of xs minus x, not necessarily in x. So always keep difference between f domain and x domain. All these extra properties are giving you this. Oh, so let's try to prove C. So now we'll apply our equation number 4 or 5. What was that? That is why we even did all this. So using equation 4 or 5? 4. Del f of x minus del f of y whole transpose y by beta del f of x. So it's not direct. You have to think for a minute why this is true. It's not rewriting 4. Just checking that I've not made a mistake. Yeah. Okay, so now what is x of s plus 1 minus x star? By the update equation, it is xs minus 1 by beta del f xs minus x star. Right? Just the definition of x of s plus 1. This is equal to xs minus x star. This is also a usual trick which is used very often. That to combine these two terms and keep this as a product. Right? Now what can I do?
What did you mean?
Sorry,
Can you use?
I've done, use nothing. I just opened a square. Sorry. Keep me honest. Sorry. I've done nothing. I just opened a square.
There is a square here.
Yeah. So wherever square is missing, please put it here. Sorry for that. Okay. Now, which terms are okay for me and which terms I should want to get rid of? If I want to prove that it's decreasing, I want to keep this as it is. somehow get a less than equal to and get rid of everything else. That's what I want. Okay, so how should I do that?
You can prove that basically the second part of there is positive, right?
Second part of this is
No,
negative. I want this to be less than equal to, I want all of this to be less than equal to 0. Beta square, yes. Thank you. The only equation I really have is here. So how do we use it? See, x star has some special property. What is the special property of x star? The gradient of f of x star is 0. So there doesn't appear anything in terms of del f of y. So I can actually handle this. Here it is just simply multiplying del of f of x of s multiplying x of s minus x of star. The same thing as here. If I put y equal to x star everywhere. So all this is nothing but greater than, so it is less than, and I get whatever I want. So this is less than equal to x of s minus x star minus 1 over beta square gradient of s. Since del f of x star is 0 from 6. Still any mistake? So essentially putting y equal to x star here. So you can prove part C rather easily. That distance is. So this is very difficult to prove if you don't assume smoothness. This convexity doesn't give you this. All right. So now we are left with taking the recursion and proving the result. Okay, who wants to attempt the recursion? Let's look back at the recursion. What is the recursion? Del s plus 1 is less than equal to del s minus some, you can think of this as a constant, times del s of square. What is your strategy? You might have seen such recursions before in life. At least give me an argument that this is decreasing. That's not difficult, but just to start. This is a recursion, right? Del of s plus 1 is less than equal to the current term minus some positive quantity. So it better decrease. Question is at what rate is it decreasing? That's all we really care about. Right? So let's just help me write it down. S plus 1 is less than equal to del of s minus 1 by beta. How much was that? Somebody just tell me. 2 beta x1 minus x star square. So that is. So let's call some constant w equal to 1 by 2 beta x1 minus x star. So what do I have? I have w times del s square plus del s plus 1 is less than equal to del s. So this implies Actually, if and only if del s over del s plus 1 multiplied by w plus 1 over del s is less than 1 over del s plus 1. Why is this true? Yeah, both of them have been multiplied and divided through 1 by del s times 1 by del s plus 1. Okay, now what? What can you subtract? What can you add? What do we want? We want at certain time this del of s to start looking like w divided by t or w divided by t minus 1, something of that sort. There is the catch. That's all I really want. W is anyway a constant. How come so far these terms are the same? So check, does this imply whether 1 by del of s plus 1 minus 1 by s. What lower bound can you put on this? While I
W times.
what did you say? Greater than or equal to?
W times.
Something better than. If I keep having them on both sides, I will be in trouble.
This idea is very confusing.
Which idea? Sorry. Okay, very good. And why? Just it slowly.
Del S is bigger than del S plus 1.
So what have we shown before? What was del S, by the way, if anybody remembers? F of xs minus f of x star. So what is del S plus 1 in terms of del S? Right? So is this true? No, I'm just moving this here. This part is less than or equal to 1. So it's greater than W. Now is it clear? What is this? This is, now you have your telescopic sum. So you go from 0 to t, what will you end up getting? That this will imply that 1 by del t is how much? T or t minus 1?
Starting from 1.
And this is how you get your answer. That del t, which is the difference between xt and x star, is behaving like 1 by t minus 1. That's what is most important. And most importantly, the step size has not been chosen by any algorithm. It has been fixed ahead of time to be equal to 1 by beta. It's very, so we don't run these big programs. It's very important for practitioners. Because every time you have to compute something, it just slows down the program. In line search or in army role, you do lots of searches, which this completely avoids. But there is a caveat, as long as somehow beta is known to you. That is a big if. It's not obvious how to select the beta. If you select something very large, you might get a poor guarantee because the step size will become very small. So the improvement will be very small. Okay. So which part of the proof you're saying is non-trivial? Sorry?
They say that I have given.
That's trivial. How many exercises have you solved? Compared to that, this is nothing. It's just observation, it's not exercise.
I know. So what like that the way you explain it, like yes, this is like that's how the proof is seems easy, but getting that idea is
So that is something that many people over many years have done this, and this is the refined way of doing things. It's not just that's why you have to refer to so many books. But surprisingly, Boyd doesn't have this proof. It's very surprising. It's the first line it writes it, all the convergence proofs you're going to give is only for strongly convex function. It defeats the whole purpose. That's very strange. We will also do strongly convex, but not before looking at all the convex problems. So this is just convex and smooth, nothing more than that. Okay, so I'll give the guarantee for strongly convex and we'll stop here today. I don't think I can complete that. There's actually a good book called, don't remember the title of the book, but by Sebastian Bubeck. It's also freely available online. I will post the link on our page. Okay, actually I can prove this because the hard part is pushed to the homework. This is really hard. We tried it last time also. It's actually a painful thing to prove. He just writes it in one line that this is true. But actually to prove it, it takes a while. Okay, so let's try to prove. So now the setting is that the function f is strongly convex. And let's call it mu. Yeah. Alpha strongly convex or mu strongly convex and beta smooth. Then gradient descent with again constant step size. Of 2 over alpha plus beta. It uses both the strong convexity parameter as well as the smoothness parameter. That is 5. F of xt plus 1 minus f of x star is less than equal to beta over 2 exponential. This is where the interesting part is. Over kappa is, I think it is some constant kappa plus 1 times x1 minus x star. Sorry? Kappa, I think, is alpha plus beta or alpha minus beta, if I'm not wrong. It's kappa. Kappa is beta over alpha. So compare the previous convergence results to this. There we had just 1 by t. Super fast, not just fast. This is exponentially 1 by t and e to the minus t is not comparatively fast. It is super fast. So all we are assuming extra is alpha strongly convex.
but you were then strongly convex. So there is no relaxation on the smoothness of
No relaxation of smoothness. If you relax, you'll get something else. For the moment, you will, yeah. You will.
Like not like
But you won't get exponential. We'll prove that also. But for the moment, this is much stronger than before. Okay. So the thing which I am not going to prove, which I will use in the part of your homework, is the following. This is actually a very standard result and you should know it. So lemma let F be alpha strongly convex and beta smooth. On Rn, then for all x comma y belonging to Rn, we have del f of x minus del f of y, the whole transpose x minus y greater than equal to alpha beta over alpha plus beta. One over beta plus alpha. This is really the backbone of the result. That this inequality is true. Just pay attention. This is the usual thing. Difference of the gradient times difference of the vectors is somehow controlled by this constant, which is alpha beta or alpha plus beta times the distance square. And see what is it's splitting as distance in the gradient versus distance in the vector space. That's how it is spreading out. It's a special inequality when alpha is both alpha strongly convex and beta smooth. Okay, so assuming this lemma, which will be in your homework, final homework, you want to prove the result. Actually, very nice, interesting, and complicated exercise. It's not simple. Okay, so proof of the theorem. From beta smoothness, what do I get? F of xt minus f of x star is less than equal to beta by 2 xt minus x star whole square. Why?
F of xt minus f of x star will just be less than or equal to f of x beta times. Okay. It's all like two steps, right? So first we have that it's first it's we know that f is strong. It's not without using strong concept. No, you don't need that.
So the integration that we wanted to do on x plus 1.
Not gone there yet. Just saying beta smoothness gives me this. Why is this true?
Oh,
Do you see why this is true? Can you tell me? It's good to go slowly. Take your time. No hurry.
Gradient of f of xt is less than equal to
What do I have? Xt minus gradient of x star is less than equal to beta times xt minus x star. Okay, that much is true.
gradient of f of x star is zero.
Yes. So on the left hand side, all I have is del f of xt. But here I'm asking for something else. Here there is a something by 2 and a product. How am I going to manufacture that? You'll have to use some other property of something. There are natural candidates to think about. What are those natural candidates, Pranav? Beta smoothness is only giving me this. This is 0. So all I get is del f of xt is less than equal to this quantity. I want to go there. How do I go there?
The lemma that we,
Which lemma?
lemma 2.
This one?
No, meaning making the long property.
This one? Even before.
Yes.
This one?
Yes, here.
Yeah,
Does it? Does the job?
if we take y to be equal to f of x star, sorry, y to be
Y is x star, so this will disappear. This will be simply f of x minus f of x star is less than equal to this quantity. But again, I'm also losing this norm sign y on the left hand side because f of xt is always greater than equal to f of xt star. Okay. All right. So now, using the lemma on the next page, which is this one, the way to think about it is it's a difference in the gradients times difference in the vector. It splits out as the square distance in the vector and the square distance in the gradients. That's the way to think about it. These constants are not very important to think about. This is the way to remember that there is an inequality of this type. You might use it 3 years from now. This is the way to remember it. So what is the interesting thing I want? Xs minus x star or xt plus. Xt plus 1 minus x star. By definition, this is nothing but xt minus eta del f of xt minus x star. So let's take the squares again. So I'll get xt minus x star square minus 2 eta del fxt times xt minus x star plus eta square del of x whole square. All right. Now, what do I have here? I can apply the next lemma on what?
So we done it that unique part you replace by somehow detail xt square or something that's you have done like 2 slides before.
Look at this, right? This is what, in essence, that thing is because del f of x star is 0. So all I will get is, see, again and again, that is very important. What is this? Del f of x minus del f of y times x minus y. What is previously here? Del f of xt times xt minus x star. So the corresponding term for x star is 0. So this is nothing but the LHS of that. You can just transport that here as it is. So let me go to here. What you end up getting is 1 minus 2 eta alpha beta. Some combination has happened here, okay, of terms. So x minus y is being combined, which is xt minus x star whole square plus eta square minus 2 eta over, it's coming from here, Because again, this term is 0 when y is equal to x star. X t. This term as well as that term where del f of x star is 0. So all I get is del f of xt. And what can I write this as? The other equality. What more can you? I proved something. How do I apply? See again. How can I apply this?
It's an integral form.
Integral, no. Where have I reached? Xt plus 1 minus x star. I've reached as less than equal to that 1 minus 2 something constant times xt minus x star whole square plus something into del of fxt square.
You have to have a term like exponential.
We'll get there. We'll get there.
Yes, for that,
Uh-huh.
you must have a kind of either integral form or differential.
Not necessary. You reached here so far. So if I can get rid of this somehow, I claim I'm done.
So you have to make it safe.
No, let's on 0. So what is this on the left hand side? This is the essentially you notice it carefully. Xt plus 1 minus x star. If somehow this term was not there, what is going on is contraction going on. This term is less than equal to 1. Then each step I'm going closer and closer to x star. And because of my f domain thing, the distance in terms of f domain is at most beta by 2 times this. This is sufficient for me. Exponential, right? This is exponential. Every time I'm halving it, let's say if this constant was, let's say this constant I get is 1/2, and this is not there. What is it telling you? The distance is halving every single time. This is nothing but exponential. This is exactly that. Sorry. And when I combine that with this, I also get that in f domain. So more difficult part is showing it in x domain. F, it follows rather easily. That is true in f domain also. So now, how do I get rid of this term?
The constant steps have to be 2 by alpha plus beta. So inside bracket becomes 0.
See, I have control over eta. I can choose whatever I like. As long as I can contain this to be less than 1, I'm okay. Right? I'm not optimizing it over. You can optimize over eta if you wanted to. But by the choice, eta was, do you remember what the choice was?
2 by alpha.
2 over. What does it do here?
It should be 0.
It makes it precisely 0. And this gives you a number which is less than 1. So this implies that xt plus 1 minus x star less than equal to c times xt minus x. So this is a very important result, that for strongly convex and beta smooth functions, you can get contraction in x domain. Doesn't happen otherwise. For convex functions, we did not show this. And from this to port it to f domain, it's rather easy. So one could argue that by optimizing over eta, you could do better. I'm not going against it. It's possible. This is just one particular choice will make sure that this is 0. I'm not claiming that this is the fastest you can go towards the x star. Because it could be that this is very small. I could possibly choose eta such that this number is much smaller. But for the moment, all I'm doing is getting rid of this one. Sorry for going way over time today. But if I had not finished it, I would have taken another half an hour.